by mixing, the delta S total is going to be greater than 0. This is not a phase change. This is not a reversible process. You know, we don't go the other direction, right? And so the delta S of the universe has to be greater than 0 for this mixing process. That's just a fact. Delta S, of course, can equal 0 if it was reversible, but this is not. Okay, so based on that, we would say everything should mix all the time. So anytime we have two things, we're increasing entropy, they should mix. But you know that the world is governed by delta G, or the free energy, and delta G only has two components, enthalpy and entropy. And so if the entropy doesn't allow these to mix, we have to examine the enthalpy, and we'll talk about both factors first. We'll talk about both factors, but we'll talk about entropy first. Okay, here's delta S total, which is also known as delta S of the universe, the system and surroundings. You know this equation. Delta S of the surroundings is negative Q system over T. Great. Here's Gibbs free energy right here. So we're going to talk about how the entropy changes. We're going to talk about the enthalpy a little bit too, and you should all know this equation. We're just going to talk about mixing, just like we talk about a chemical reaction. So we're just going to write down the Gibbs free energy for our mixing process. No reaction, no phase change, nothing else going on. And so we need to examine if there's enthalpy of mixing, and enthalpy is also known as what? Heat, that's right. Entropy is going to be disorder, and so we're going to examine what it takes in terms of disorder as we make this. So speaking of the heat, or the enthalpic part, let's call it enthalpy, but has anyone ever here made a salt solution in water? Has anyone ever made like a 5 molar sodium chloride solution or a 1 molar lithium chloride solution? You take water, right, and you dump a bunch of salt in. What happens to that water? It gets warm. Who said it gets warmer or colder? Right, A for the day. That's the enthalpy part. And so, of course, the entropy increases when you make a salt solution because the solution gets more random. But there's a really strong enthalpy of mixing too, and that's why the delta G for dissolving sodium chloride is really largely negative. So we'll examine the heat of mixing for polymers, but we're going to start with the entropy. Okay, so if we want our polymer and our solvent to mix, this is a homogeneous polymer solution. By definition, looks pretty homogeneous, right? And how is this different from that salt solution? Or if I mix two small molecules? If I mix two small molecules, what would happen? I wouldn't have these guys, right? I wouldn't have these macromolecules. This is the cool part about polymer solutions, because those chains, or those macromolecules, tug on one another, right? They can be entangled. That's what makes polymer solutions really viscous, right? This is what makes oobleck work. And if you watch my videos, or the videos I have in this lecture, the only reason why those solutions are viscous, or we see interesting things happen, or we have self-siphoning fluids, or you can walk on oobleck quickly, is because these polymer chains. If I just mix small molecules, viscosity is nothing special. It's nice and low. It just behaves as a liquid. In some cases, we might call this a non-Newtonian liquid. Does anyone know what the vocab word non-Newtonian means? Okay, you can look it up. And small molecule solutions give Newtonian liquids. And so that's just a vocab word that you'll hear about in the future. All right. If these are miscible and if everything works out correctly, the delta S total is going to be greater than 0, so the entropy is increased, right, because we're mixing, and the delta G mix needs to be negative. What do you know about delta G? When delta G is negative, what happens? It's thermodynamically favorable, right? If delta G is 0, you're at equilibrium, nothing's going to happen. And if I compute a delta G and it's positive, what do I know? It's not thermodynamically favorable, and so nothing will happen. No matter how long I let this polymer and solvent sit together, if the delta G is positive, they will never mix. It's thermodynamically impossible. Okay. More vocab words. Mean field assumption. So mean fields are really interesting, and they're part of polymers, and so I'll just let you read this definition, that even though this molecule right here, it's got this solvent neighbor, it's got this polymer neighbor, it's got this polymer neighbor, this molecule has of solvent has this solvent neighbor, this polymer molecule, this polymer molecule. They're all sort of different, right? It's a homogeneous solution, but if we look at individual molecules, there's little differences. There's little differences in the nearest neighbors. And so the mean field assumption is that we take all of these little different microenvironments and we average them to get one mean field. So one polymer experiences one environment on average, and one solvent experiences one environment on average. And we do that because we know our polymer solution contains polymer and solvent. And we'd really like to compute the environment of that polymer and solvent, but we can't take, solvent 1, solvent 2, solvent 3, solvent 4. It's impossible. Remember, we're talking about molar quantities times 10 to the 23rd. We can't do 10 to the 23rd calculations. So we have to make this mean field assumption, and you can just read it. Each molecule is assumed to be acted upon by a potential that is an average taken over all the interactions. We know that there's little differences depending on exactly where you are, but we're going to take an average of what the solvent feels and an average of what the polymer feels. It's sort of like the median income of the United States, right? That's a number, it's computed. But we know that there's variations in income depending on exactly who you are. Same thing here. Depending on who you are, the solvent will experience slightly different environments, but there's an overall average. So hopefully you remember this mean field because it's a very powerful scientific technique. Okay, you can wake that person up right there. Wake him up. Thank you. I don't sleep in your class, so you don't sleep in mine. Remember that, and we'll get along. All right, entropy of mixing. This is a mixed system right here, and so we have to examine just mixing of these spheres or mixing of these circles, but let's assume this is in 3 dimensions. So the entropy, we are going to take this thing called a Boltzmann distribution or a Boltzmann equation. Does anyone know what Boltzmann is? Okay, I'll just assume that you do. You can look it up. It's on Wikipedia. K is the Boltzmann constant. S is the entropy. And then this capital omega right here is the total number of ways that these molecules can be arranged. When we're at the molecular scale, that's a lot of ways, right? Say you have 3 pennies on this desk, right? Or say a penny, a dime, and a nickel, and you want to put them in a line. You can arrange those a certain number of ways. Say you have 10 coins that are different, and you want to arrange them a certain number of ways. The number of ways increases by what factors? Anyone know the math? That's right. So someone said factorial, which is the math of combinations of ways. And so we're going to get to factorials in a second. But it's a lot. You know factorial is a big number. And if you don't know what factorial is, please look it up. You've seen it. All right. So we have the entropy as Boltzmann's constant. You could just look that up because it's a constant times the log of the number of ways that you can arrange these things. Okay. So it's hard to compute it unless we have a model, right? Liquids are disordered. So if you look at how all the molecules are arranged in a liquid, there's a lot of things going on there, right? So it's hard to imagine what that is. And so we need a simplified model. And a model is a very powerful term because a model is a physical assumption that you can use math on and compute mathematically. So does anyone have a really good idea of how to model this problem? What assumption could we make? This mixing problem. We've got a liquid, all disordered, lots of stuff going on. So what's an assumption that we could make to really simplify this thing? Does anyone play Connect 4? Chess? Checkers? What do we use in those games to make them easier? We use a grid, right? We use a lattice so we know where to put the pieces. Imagine playing chess without a chessboard. It would be hard. People could make up all sorts of rules and put pieces wherever they want, There's a lot of different possibilities. But if we start with the chessboard, which is also known as a lattice, we can do math on a lattice. So you know that chess has been solved because there are certain numbers of rules, and computers can play chess because they're good at math. And so we're going to use a lattice model for our liquid. So you'll have to bear with me here, and you'll have to think about this in 3 dimensions, right? A liquid, we can assume in a hard sphere model, which is another assumption, you have a bunch of tennis balls, and you just throw them into a basket, and that's the order of a liquid, right? They stack up however they want. There's little spaces between them in 3 dimensions. Now we have our chessboard, and so each solvent molecule is going to occupy one of these lattice sites. So vocab word here, lattice. This is a 2-dimensional lattice, X and Y. We can have 3-dimensional lattices, also known as crystals. Those are in X, Y, and Z. And so that's why we can solve the crystal structure and other things like that, because we know where everything's supposed to be. So this is a really big assumption for what a liquid looks like, but we have to start somewhere, or else it's really hard to make progress on this problem. So we're going to use a lattice model for mixing. We have component 1, we have component 2. They each have to occupy a lattice site. So anytime you see lattice model, think of this. And we use lattice models for all sorts of things. Because we have a lattice, we can now compute the entropy of mixing small molecules of equal size. I'm adding assumptions as we go, so now they're equal size, now they're small molecules, so they're all circles, they're all equal size. And so if we start with the number of A molecules, so the number of type A, so you should know what N is. N is number, sub A is A. I don't know whether A is red or blue here. And the number of B molecules, then assume that there are no holes in the lattice, so there's no empty space. And so the number of sites in the lattice, N naught, is the number of A's we have plus the number of B's. You just count that up, you know that's true. You can get the lattice size, you can compute it, you can do whatever you want. So you take this, take all the chess pieces or all the checkers off the board, and then put them back on randomly one at a time. Just throw them back on. How many ways are there to put the first molecule on the lattice? So if we clear the checkerboard and we just want to put one red or one blue on there, how many different positions can we put that first checker on there? N naught, right? That's the size of the lattice. We can pick any of the N naught positions. Good. So it doesn't mean just because in this configuration we've got red in this circle, and the next time we could have red, we could have blue. I don't know. We have distribution of possibilities, right? The Boltzmann distribution. But there's N naught first choices, okay? And we can think about how many ways are there of putting 2 molecules on the lattice, 3 molecules, 4 molecules, 5 molecules. We can think of all the combinations, and then we start to get into the math. So when you study this at home tonight, you can say how many ways are there of putting 2 molecules on the lattice. The first molecule is N naught ways. The second molecule is N naught minus 1 because we've already taken up one site. So there's N naught minus 1. The third molecule is going to be how many ways? N naught minus 2. The fourth molecule is going to be